And now I would like to announce our last speaker of this session. I would like to invite to the stage Robyn Woollands from University of Illinois, and she'll be speaking about light pollution versus climate change. Are cancellations always bad? Thank you.
Well, good morning, everyone. Thank you for the introduction. So I'm at the University of Illinois, Urbana-Champaign. I'm an aerospace engineer. Before I start the presentation, I would like to acknowledge the technical work that I'll be presenting here was completed by my PhD student, David Stanley, during an internship at JPL with my JPL colleagues. So I worked at JPL before moving to IAUS. We currently have a paper under review in the Journal of Spacecraft and Rockets called Enabling Space-Based Computed Cloud Tomography with Mixed Integer Linear Programming. So what I would like to present today is a moral dilemma, a discussion of a moral dilemma. What is more important, predicting extreme weather events or keeping the skies quiet and dark? So if you take a look at this figure here, this is showing all the billion-dollar extreme weather disasters that occurred in 2022 just in the USA. So if you count the number of circles on this map, you'll actually find that there are 18, and we have extreme drought on the West Coast and fires, severe thunderstorms, hail, cold fronts in the center of the country, even in Texas, and hurricanes and tornadoes in the southeast. And so $18 billion weather climate disasters just in the US. This doesn't take into account the current fires in Canada, flooding in South Africa, and so on. So clearly, there's something that we need to consider here. So this figure here shows on the x-axis the months, January through December, and on the y-axis, the number of events per year, these billion-dollar events. The data on this figure is from 1980 to 2022, so 42-year time span. And you can see that the last few years are the color-coded ones here. So if you look at 2022, we've got 18 billion-dollar weather events here. We had, 22 of these billion-dollar weather events in 2020. So clearly, the last few years are well above the black line, which is the average. And these are causing loss of life, loss of livelihood, and so on, and a lot of expense to the country. So what do we do? Well, in order to better predict these events, we need to have better climate models. And how do we improve our models? Well, we improve our models by observing clouds, and this is best done from space. And this will help us to better understand the water circulation in the atmosphere, how much water is about to be dumped on a city, and so on. And this will help us to improve flood prediction and give early warnings. So one of the proposed techniques is cloud tomography or computed cloud tomography. So this is recreating the volumetric properties of clouds using multiple images from multiple angles. These images are fit to 3D radiative transfer models, and we use these obviously to predict climate and weather and extreme weather. So cloud tomography is very similar to a CT scan that you might receive in hospital. So here at the top, you see our patient about to undergo a CT scan. We have a source, which is in this case X-ray. Behind the patient is a detector, and so the beam, we know what the beam looks like going into the patient. We can see what we detect on the other side of the patient, and this helps. Well, this enables a 3D slice through the patient to be obtained, and for doctors to know what is inside the patient in that volume. So cloud tomography is very similar. We need a lot of high resolution images. And we need to get these images over a large range, angular range, so we can investigate what is inside a cloud. Now, there are different ways to do this. There's active, which would use lasers and radar, and passive, which uses reflective sunlight. Here you can see a plane flying in the vicinity of a cloud using reflected sunlight to perform cloud tomography. Now, why is this best done from space? Well, clouds vary rapidly, so they're varying on the order of tens of minutes. And so if you fly a plane around a cloud, or you do you have one source doing the cloud CT instead of multiple sources, it takes time to fly around and collect multiple images from multiple angles, from the ground or from a plane. So this leads to errors, temporal errors, which propagate into models. And again, it's one of the greatest causes of uncertainty in climate models. Here's an example of a satellite, the Terra satellite that was launched in 1999, containing the MISAR instrument, which is doing cloud tomography. It's a single source satellite. So what we did, my student and I and some of our JPL colleagues, we proposed a mission concept to use multiple satellites in low Earth orbit to try and do this cloud tomography and see, well, we didn't actually do the cloud tomography, we engineered the mission and to see how using a constellation of satellites could improve the number of measurements made in a large angular range compared to a single satellite like the Terra satellite. So here you can see our constellation. We converged on a string of Pearl constellation here. Each of these satellites, do I have a laser? Each of these satellites is separated by a minute or so. The field of view is 7.5 kilometers squared. Pixel resolution is 5 to 30 meters pixel resolution. Each of these satellites has a camera on board with agile pointing capabilities. So our problem that we were solving as engineers was, how do we optimize using mixed integer linear programming the slewing and pointing of these satellites in the train to maximize the number of observation, or to maximize the range of over which a particular point in the sky or cloud is observed. So if you take a look at the figure on the right hand side, this blue shaded area is the region that the satellite, the string of Pearl satellites could look at any given time. Now the yellow dot, which is marked with the 7.5 kilometers, I guess you can see it, marked with a 7.5 kilometer tag, that is the field of view at a particular instant when all those satellites are pointing at the same target. The red shaded region here is 1 minute's worth of sweeping of the push broom satellite, which was the Terra satellite, an example of the Terra satellite that you saw on the previous slide. So these these small sets that we proposed for this mission concept are similar in size to the SpaceX Starlink satellites. So using this methodology, we did some studies to compare how the imagery, well, how the data obtained using this chain of CubeSats compares to the push broom. And what we found is that using this chain of satellites to autonomously and simultaneously measure cloud objects, we're able to get 59% more images over a range of an angular range of between 140 and 150 degrees compared with the single satellite. So what do we do from here? So as I mentioned, there are active and passive methods to do cloud CT. Luckily for astronomers, for now, cloud CT is done passively using reflected sunlight, and it's only done on the day side of the planet. Data downlink will be done on the night side. Now, if we could use active sensing, this would open our other eye, and we'll be able to do science 24 hours of the day. But this does require a lot of power. So having a source in orbit would require much more power, of course, than using just reflected sunlight. And back of the envelope calculation reveals about 100 meters squared worth of solar panels, which is comparable on order of magnitude with the Blue Walker 3 satellite. So if we were to have 10,000 of these Blue Walker 3s flying around doing cloud CT day and night, this would be a huge problem for astronomy. So in conclusion, satellite constellations can improve our ability to predict severe weather events. The cloud CT mini constellation concept is in its infancy. This picture that I've taken here, the top picture is from Zentrum for Telematic, which is a European company that has recently received a huge grant from the EU to do the cloud CT mission. Many other climate phenomena could be studied from space as well, not only doing cloud CT. So for example, we could do early warnings for ocean waves, tsunamis, early warning for fires, things of this nature. Currently, cloud CT only uses passive sensing and it only covers the day side, but if we could do active sensing, that will provide true global coverage, and the size of these satellites may be comparable to the size of Blue Walker. So thank you for your attention. I'll be happy to take any questions.
Thank you very much for a very interesting presentation. Do we have any questions online? No. Okay, we will take the questions from the audience here.
Good morning, Gyula József from Max Planck Institute for Radio Astronomy. Thanks a lot for this wonderful presentation. I've actually two questions, and actually this makes one think of, obviously. Number one, the view graph with the disasters showing the time dependency of what was it, multi-billion-dollar casualties. Was this corrected for inflation? I'm sorry, this is a scientific question.
I assume that it was. It's a good question, but I assume that it was, yes.
Then the second one is true 24-hour coverage is done with active sensors or active elements. How much of a requirement is this time coverage to have an accurate picture?
Yeah, that's a good question. I mean, I'm not a cloud scientist. I'm an engineer who engineers a mission, but I would assume that the more data we have, the better we can do, right?
Of course.
So, but yeah, so I guess I would have to defer that question to a cloud scientist to give you a definitive answer.
Yeah, there are a few other questions.
Okay, okay.
Maybe we'll talk after.
Yeah, sure.